I'd like to introduce our speaker, Dr. Lewis, who's a professor emeritus at Johns Hopkins Bloomberg School of Public Health. His research includes Bayesian methods, clinical and field studies, health services research, genomics, and survey methods. He has a number of honors and awards over his career. From 2018 to 2020, he served as an expert statistical consultant to the Center for Drug Evaluation and Research at the FDA. From 2013 to 2015, the Associate Director for Research and Methodology and Chief Scientist at the Census Bureau. He's an elected member of the International Statistical Institute, a fellow of the SA, the American Association for the Advancement of Science, and the Institute for Mathematical Statistics, and a number of other awards and honors over the course of his distinguished career. And so I'm very happy to be able to introduce Dr. Lewis as our speaker, and the title of his talk is really intriguing. I'm really curious to see what he's going to say. Big data, missing data, and transportation. And so Dr. Lewis, please take it away.
Thank you, and thanks for the introduction. I'm happy to participate remotely and frequently, or not frequently, but regularly end up in San Diego area. And so at some point I will be there again. The subtitles of this are, as you can see, it's not all about big data, but some of it is. And then the one I crafted and kind of enjoy is transportation without representation is travesty. And that's borrowing from the taxation without representation is tyranny. I'm going to do what I guess could only be called a high level breeze through several aspects of using of big data and other things that are related. Hopefully you'll be motivated by some of it. Maybe you'll be frustrated by my not having taken a deep dive, but let's just go and see how it goes. So let's first of all see if I can advance this. Okay, here we go. I found the right way to do it. So I'm not going to read all of these things, but big data is, depending on which way you like to do the plural and singular, they surely represent opportunities and challenges. And I'm going to focus just on a little piece of issues with big data, obviously not everything. The importance, if you're going to try to do inference or something other than just general prediction, the sampling plan is important and the reference population is important. These are, if you'd like, traditional values, I guess I would call them. And give some theory and examples and then a little guidance and open it up for hopefully some questions and comments. So these are quotes that you've probably seen over time, Marie Davidian and I having one in the Science magazine several years ago. I won't read it again, but the idea is that big data is going to drive our future. We're not the only ones saying that, obviously. It's datafication of everything. The features of big data, and this is the usual VVV, volume, velocity, variety. Usually organic creation, not terribly curated, although big data certainly entails everything, including well-curated data. Passive data collection in general, not always, and instability. And sort of the traditional statistical world, I think, has gotten over it, now has to cohabitate with the data-centric world in this sense. And I really kind of still enjoy this Wired magazine thing from, what was it, 2008. The end of theory, data deluge will make scientific method obsolete. I don't think so, but it certainly has changed things. Another one that I enjoy, and then I'll stop doing these things, but this is again a long time ago, or 2015 anyway, that Apple and IBM may someday keep you healthy. So I'll just say, take a daily big data and you may be okay. So the point is, though, that, or my point anyway, is that big data does not imply big, relevant, or valid information. It doesn't deny it, but it doesn't imply it. While big data has produced some interesting and important predictions and associations, a lot of care is needed to move from these to explanation, causation, and transportability, which I'll get to again. And the issues include, of course, the instability of the data generating process, bias and confounding, lack of representation to an intended population. These are hardly new ideas or not necessarily novel with big data. And there are a lot of modern techniques, of which I'll hint at a few today, that can improve validity, but probably unlikely to be fully successful, and yet better than not doing. So there are rules for big data, but I personally don't want to give up on the idea of well-curated data being needed in conjunction with, or the other way around, big data in conjunction with well-curated. So a golden oldie, of course, is that the sampling plan is very important if you're going to try to do inference of any sort. There's always a sampling plan, even for big data. And certainly the official kind of prospective ones are things like standard randomization, stratified randomization, cluster, snowball, all of those kinds of things. There are certainly sampling plans that could be called haphazard, convenience, in sequences they arrive. And then the one I have here well, except that I've got to remember how to advance things, which of course I didn't do. I apologize for my incompetence. And then you can have that, I have no idea what the sampling plan is, but I do know that there is one. And the usual challenges of any process of collecting data, that selection effects, informative dropouts, and other types of missing data affect sample representation. Nothing new having to do with big data particularly, but still important. But it's also true that if you know the sampling weights, even just for the observed sample, you have a representative sample of some population. The problem or the challenge is you may not be able to identify that population, but there's some inference that can be done in that sense. So I'm not by any means do much technical statistical hill here, and even this is not what I would call in any way highly technical. But the traditional sample survey, you identify a population and a sampling frame. You develop and implement a probability-based sampling plan. And you conduct, if you're being just a traditional survey sampler, a design-based analysis. The data, the underlying values, the Y's are fixed, and the sample inclusion indicators, the yes or no, I made it into the data set, are the random variables. And they follow a joint distribution determined by the sampling plan. And if you know those probabilities, those propensities, the sample is representative. Then you can do a model-free standard analysis, which I'll have in the next page. The standard error can be very large for this. So in modern thinking, even at the US Census Bureau for many things, you bolster that design-based approach with modeling coupled with it so that you can stabilize and do other things. But if you don't have a design sampling plan, knowing the propensities is challenging, not completely hopeless, but challenging. So here's a very artificial example of what I've been saying. You're trying to estimate the average length of stay for hospitals in a specific domain. We have 5 hospitals. And here's, if you only knew it, the true underlying population size in terms of patient size, and what the percentage of the total hospital population is for these various hospitals. I think I got the math right. Way over here on the left, and maybe I should have put it closer, are what your sample is. And the point here is that I made it, in fact, so that the sample percent representation, for example, in hospital 1 is 20%, but in the population, it's only 10%. This is not a self-weighting sample. It's got, in that sense, disconnects between the percentages over here and the percentages over here. And here are the relative propensities for getting into the data set. So it's not self-weighting. Some of the relative propensities aren't equal to 1. In fact, none of them are equal to 1. It is representative, though, in the sense that if you know these propensities, you can produce an unbiased estimate of things. This is at least something that Niels Keating and I pushed, that is, doesn't have to be a self-weighting sample to be representative. You just have to know these things. So I'm giving you on this next slide 3 choices for weights that you might use in the sample. The minimum variance one uses reciprocal variance weights and will always produce the minimum variance estimate. And at least if you've got the standard errors from the data set, and we have them here, you can produce the minimum variance estimate. And I'm giving it a relative variance of 100 because it's the smallest, if you'd like. You could do an equally weighted analysis, and the only justification is I want to do an equally weighted analysis. I want to give each hospital equal weights. So there they are. The mean that you get is that, and you've paid for that with variance inflation by 30%. If you have those sampling propensities on the previous page, you can do the unbiased estimate by using what are now these sampling weights, which are just the normalization of those relative propensities. You get what is presumably an unbiased estimate of the overall length of stay, and you paid for it with a fair amount of variance inflation, 72% if you'd like inflation, but you can do it. I hate this idea that I have to keep paging down here to do this. Did I capture everything? And one of my points is, and I'm glad I got back to it, is that there's really no free lunch in statistics. There are a wide variety of reduced price lunches. If you want minimum variance unless the sample is self-weighting, you're going to pay with bias. If you want unbiased and less the sample is self-weighting, you're going to pay with variance. And you may want a compromise estimate. I'm not saying 2020, 2020 is the right one. It pays some variance inflation. It has a little bit of bias, but it might be in the sweet spot, at least for the sample size we're talking about here. So one slide of formalism and maybe another one a little bit later, but not many. Translating what I had previously to a more formal presentation. Here are these Y's that are again sitting there unknown, but not random, at least in the traditional finite population thinking. You draw a sample and you do it with selection probabilities pi k greater than 0. You can also produce the joint pi kj's about two things being in, but I'm not trying to trash this up with a lot of notation. You might want to estimate the population total. You might usually want to estimate the population average. And you do it with Horvitz-Thompson estimates. You just take the observed data now. These are only the Y's that you get to see, not surprisingly. Divide by the propensity and add it up. For the average, you do the same thing, and you then divide by just 1 over the pi k's. This is an unbiased estimate. This is almost unbiased. But of course, you need the pi's to do it. An alternative that I'll be hinting at a lot is you could just do a regression approach using a flexible function of the pi's as a covariate, along with possibly other covariates. And the goal is to make the selection process ignorable. Here's one way to make it ignorable, but a properly constituted regression with very flexible functions of the pi's can do it also. And Rod Little, not only I'm not good at navigating with this. Rod Little in 2012 and in many other places has lots of discussion of doing that kind of thing, of building flexible models with the propensities. So if these pi k's are correct, the estimate's unbiased and you don't need a model for the y's. But producing them can be complicated, and especially complicated if non-response imputation and so on need to be accommodated. And the approach that seems to be quite modern and is really, if you'd like, the stem cell of doubly robust methods in causal analysis, let alone in census areas, is to augment this. And I'm not giving formulas for it here because I just want to give a high level thing, is to augment it with a standard old-fashioned statistical model, but also then do the Horvitz-Thompson on the residuals and get what is called these days a doubly robust estimate. But of course, validity depends on the pi's, and without a formal sampling plan, it's difficult, if not impossible, to find them. However, we have approaches that can help, and I'll get to some of those. So there are a lot of discussions in the literature and elsewhere about are non-probability samples informative. One view is very strict constructionist, that you can't use them for estimates because the weights aren't available. And the debate is really about whether or not you can get representation. So I posed at one point, and Niels Keiding and I at a paper, would you rather have a 60% response rate from a well-designed and conducted Gallup survey, or a 95% rate from a self-selected group? And if I could see your pictures, and I can't, some of you might be saying, how do you get a 95% rate from a self-selected sample if you don't even know how many people might have get in? And the answer is, who knows? But the point here is that the 60% from the Gallup might be preferred anyway, because at minimum, you have some characteristics in general about those who did not make it in, because it was a sampling frame that was used. And so you have some chance to do some adjustments that can help things out. The non-probability has potential because there may be other data, covariates and other things, big data, that can be used to develop reasonable weights for some reference population. So the idea that, certainly not unique to me, use all data, big, small, in between, to help identify the population and compute weights, conduct sensitivity analyses. And it's somewhat of an analogy to clinical trials, where most causal questions aren't protected by randomizations, are not intent to treat, but careful causal analysis can be valid. So here's a sort of a framework and a very nice paper in 2017, which gives a nice set of analogies and parallels between causal inference and survey inference. And I'm just putting an extract of a few things here. And one is, we have, for a clinical experiment, for example, we have participants that are then randomized to treatment. In a survey, you're a member of a reference population. It might not be a human being. It could be a unit of some sort. The randomization is into being in the survey, but there's a direct parallel between these being randomized experiments in that sense. And the causal prerequisites for the surveys are essentially the same as for other studies. Exchangeability of no confounding or all confounding variables accommodated. Of course, we all know the all may be a challenge, that there's a chance for everything to be in there, and that the distribution at least matches the target population in a distributional sense, at least gets close enough. And this idea of transportability, which I don't know if it was coined by Pearl and Barenboim, but certainly they use it a lot, is careful analysis of directed acyclic graphs and other things to try to come up with necessary and sufficient conditions for various settings to be able to transport from the data you got to other populations, or to a reference population from which it came. And Pearl and Barenboim and others have what are just dizzyingly complicated representations and language for doing this. It's Pearl's do calculus and other things. And I can say, not only with this 2014 version, but others, if you're interested in reading it carefully, just rest up before you do. So a few more data examples here. And this is just looking at random digit dialing versus internet surveys. Again, this idea of organic versus not. And so on the top here, this is average absolute error between what was at least determined to be the truth and what you get from the survey. And so here are both telephone and internet surveys, but they're probability samples. And a higher bar is bad. It's an average absolute error that's worse. And here are 7 non-probability samples. And yes, it's true, at least for this possibly selected group of studies, they're all higher than the probability samples one, whether they be telephone or internet. And down here, it's the same sort of idea. These are the probability samples for telephone, for internet, and non-probability for internet. And again, the x-axis in this case is absolute error, or absolute bias. And it's not like the probability ones have no bias. The histogram is not just all crowded at 0, but compared to the non-probability ones, not only is there less heterogeneity in the score, but this one has a much longer tail, including one that obviously maybe one that was used to predict some election or something like that. But this is at least showing in an experimental sense, quasi-experimental at least, that again, there's an advantage to the probability sampling idea. Xiaoli Meng has many cautionary tales, and he put some of this in a discussion of one of Nielsen's and mine's paper that I referenced near the end, so you'll see the full reference then. But it's laid out in very much more detail in his 2018 really wonderful article in the Annals of Applied Statistics, Statistical Paradoxes in Big Data, the Law of Large Populations, blah, 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 blah. So it's a typical Xiaoli set of phrases. So the idea here is to show you just how challenging it is to use non-probability samples to make progress. Consider you're looking at mean squared error, in other words, variance plus squared bias, in a large reference population. And you're comparing how well you do if you just take a very small, relatively speaking, simple random sample, and you get an estimate with the sample mean. And then you do a selected sample, which isn't randomized, and where there's a correlation between the true underlying Y's and the propensity to be included. And the example he uses is just a correlation of 0.05. I won't give you the details. And you don't know you don't have the map that gives you how these correlations map to the underlying Y's. So if you want to have the selected sample's mean squared error be less than or equal to this teeny simple randomized sample, the fraction of the finite population that you need to sample for this case that I'm giving you is 20%. Great, you need at least 20%. So if you're doing an estimated mean from a reference population of 50 million people, you need the selected sample to be at least 10 million to beat this silly 100 sample size random sample. It shows how you really have to be very careful. If you have good information on the correlation, or at least some information on the correlation to unlink this, you can then very much improve the performance of the selected sample. But in this pure case where it's underlying and you don't know it, you get in trouble. We also can look down here for some recent metrics on getting an idea in a sample of what the selection bias might be. And these are for COVID examples, but the methodology holds more generally. So let's see how I'm doing time-wise. Okay. This is old again, but I don't mind old. I am old, and also they still are informative. This is a study looking at the relation between self-reported voting rates and how they actually voted. And of course, with voting, at least, there's a form, you could call it big data, although it's really just administrative records, which are the voting rates for a given area that are known, not person by person, but what the overall participation is. And in this 2008 survey, 78% of the respondents reported that they voted in the presidential election. But if you look at voting records, not just consolidated records, it was like 57%. And if you try to adjust for the standard prediction of participation and do a weighted adjustment and so on, you can only account for about half of that discrepancy. And so it's another challenge that the associations didn't transport. These things that are definitely associated with voting and so on didn't help solve the whole discrepancy here. So I'm getting some negative things, I know. generalizing clinical trials. And there are several approaches, and of course, they don't have to be specifically applied to clinical trials, but the example that I'll give is. You can sample by weighting sample inclusion probabilities. This requires that you have some idea of a reference population. You can use this idea of flexible regression modeling and machine learning with propensities as some of the regressors, and then weighting the model predictions that you get to whatever reference population mixture you'd like to do. And again, this combination of the two for double robustness, targeted maximum likelihood, and so on. And the regression approach can be effective using data from the observed sample, and we'll get back to that a little bit in some slides that are coming up. But the idea here is to get away from either the pure form of just reciprocal propensities or standard modeling, but try to combine the two with the goal of making the selection process, whatever it might be, as ignorable in the statistical sense as you can, so that you can at least reduce the effect of selection bias, not to, in any sense, think that you'll always be able to eliminate it. So here's a clinical trial example where the study is looking at suicidality rates, and the darker bars here are from clinical trials, randomized trials, and the gray is from a survey, the Youth Risk Behavior Survey. And these are suicidality events per 100 subjects. I'd rather wish they'd use patients or participants. Anyway, you can see that in every one of these cases, for all RCTs and the adjusted survey for the same demographics and other features of the surveys of the clinical trials, a big discrepancy in the rate. If you just go excluding the high-risk clinical trials, first of all, you would hope that the rate goes down in the clinical trials, and it does a bit. Again, a big discrepancy. And even when you just focus on the high-risk clinical trials, which again, it's not good for the world, but it should be logical that there'll be a higher rate of the event, it comes a little closer. But even with adjustments for whatever was available and being conducted by successful, sophisticated statisticians, you can't get all the way. Now, I don't have on here what happens if you don't do any adjustments at all. The discrepancies are obviously much bigger, but you don't get in anything that you'd call a good match here. So one of my colleagues and colleagues of his, Nilanjan Chatterjee, has a nice paper in 2016, and he has others that have followed. The idea here is that you have an internally valid, not necessarily small, but not necessarily gigantic study, a randomized trial. And you have a large study that may not have measured all of the attributes relevant to the internally valid study, but you have some. And so the big study has at least information on the joint distribution of a subset of the internally valid study variables. And it also has other information on outcomes and so on. So one idea is to constrain the small study estimates to be compatible with the externally determined relations. In other words, weight the small study to be at least as well as you can do the representation to be representative of the bigger study that isn't quite as fine-grained in other ways. And it's very analogous in my mind to stabilizing interior estimates of a contingency table by benchmarking to marginal distributions estimated from other data. In other words, stabilizing the margins. Or another analogy that I'll give to this is to use external prevalence data to allow case control study to actually estimate a relative risk. Whether they estimate it well or poorly is another question. It all depends on how relevant these prevalence data are. And the key for this being successful is that stochastic features of the external data are sufficiently similar to those for the small data set in order to reduce the mean squared error by reducing the variance, by relying on the bigger data set, but not as fine-grained and not as detailed, to at least stabilize some aspects. And so I could spend the whole talk on just discussing this paper, but instead I'm simply giving you at least what hopefully will be for some motivation to peek into some of these papers and see some of the details. So that kind of approach is a little bit like compromise estimation in that you're combining a, let's say, unbiased or at least low bias study that may or may not be big, but let's say isn't gigantic, with another study to strike a good trade-off. And so here's a little more of a formal aspect of that. But the general idea in statistics actually is to combine a low variance estimate. I'm going to call it a model as a function of paras, i.e. parameters, and a nearly unbiased estimate. Let's call it an unbiased estimate. And the idea is, I'm sure you all have done it. Well, anybody who's ever fit a regression and has stopped when the adjusted R squared starts going down are already trading off variance and bias, because you're admitting to the fact that you're not putting in all variables, and therefore your regression is probably a little biased, if not a lot biased. But you're doing it because adding more variables is going to inflate the variance too much. And so I'm not doing the regression case, but just the more standard, if you'd like, combining two estimates by taking the weight on them. And the idea is to give a weighted average of B on a model, which presumably, although biased, is smaller variance, and 1 minus B on the unbiased estimator, where B is between 0 and 1, and it's the relative size of the mean squared error of the unbiased estimate to the total mean squared error. You may say, but I'm talking about unbiased here. Why did I do this? To make it the general formula, I put MSE here. But if it were truly unbiased, it would just be the variance of that unbiased estimate. But the general way to think about it is MSE over MSE plus MSE. And so the idea is B will be, now I'm hoping that it won't skip the page, but we'll see. I now knew what to click. B increases, not surprisingly, with the increase in the MSE of the unbiased estimate. It's going to give more weight to the model, stabilize the estimate a bit, pay a little bias, no question about that, because the mean squared error will be helped by reducing variability. But B decreases when you get a decreasing MSE of the unbiased thing, because it doesn't need as much help. Bias becomes more important, variance less important, so let's give more weight to the unbiased estimate. And the idea of how to do this, in other words, how to know what these MSEs are, especially for the model, really almost always requires a more of a Bayesian formalism. But this kind of just taking a weighted average of two estimates is a basic principle of statistics. So here's an example of that and a few other things. And this comes from a couple of papers, but the 2015 one, observed best prediction, and then one that Nick Henderson and Ravi Varadhan and I have in recent JASA. And the idea is, well, how should you estimate that B? Now that I'm getting along in the talk, I can actually go back and forth more easily than I was before. How to get an estimate of the B. And I'm not giving you the formalisms here in any sense, but if you do maximum likelihood, you're minimizing the variance, just like we did for that sample survey. And if the model that you've used in that previous slide is properly specified, it's the optimal way to go. You're reducing the variance, you're minimizing the variance, and there's no bias, or at least the bias cannot be improved. But Chen and al decided that maybe we shouldn't rely so heavily on assuming everything is completely fine, and said, let's actually find the B that it gives best predictions as opposed to minimum variance, and uses the data to come up with what the weight should be to give the best observed minus expected kind of thing. And it will always give B, will always give those units that have a big B, in other words, the ones that really care about the model, will have more of a role in estimating the model than they were under MLE. So Nick and Ravi and I decided, well, let's try again. Let's go further and do a compromise. The idea is maybe one should compromise between these two. I suppose our goal was, why not have a paper? But I think it turns out to have been a very useful thing. Let's do a database compromise between the MLE approach and the observed best predictor approach. So it's compromising between models that themselves compromise, and I guess we could call that rinse and repeat. And you can decide down here if you want to do compromise, but maybe we've reached the convergent point. And so here's a small example of the idea. We're estimating things in 50 units. Think of them as hospitals. The example is really in the paper is more on individuals. But imagine the case where the outcome is, I don't know whether that's blocking your view as well as mine, but outcome is correlated, in this case with sample size, but more generally, it just correlated with something, just like in the Meng example. And here's a case where the sample sizes for the 50 units are uniform in the log scale. And here it's just two types of units, big sample size and small sample size. And so you can look at both of them, but I'll just do this one. If the correlation is 0, the model that you've used in that modeling statement is exactly correct, because you've left it out of the model, but it's not its value is 0 anyway. And it's no surprise that in terms of the average mean squared error, the MLE, and we put in here REML too, but they aren't very different. You can't beat them because they have minimum variance and they're unbiased. The observed best predictor pays a fair amount in this case, and the compromise, it's no surprise, it compromises, but at least it does reduce from that inflation. As the correlation increases, and you can decide in any application whether 0.6 is already beyond anything you can expect, but you begin to see that both the red line and the blue line cross over and become an improvement, where the blue is never worse than the red. Both red and blue are worse than this if the model is correct, or at least not horribly bad. Same sort of thing for the 2-point sample size. And the point I want to make and do make is that first of all, you may have an underlying structure that is more complicated than just association with sample size. You may have a lot of covariates. If you trust your model completely, you'll use this. You should always build as robust and as good a model as you can, but then, at least in my view, paying a little bit when the model was actually correct to buy some insurance when it isn't correct is not a bad idea. How much to buy depends a lot on the application, but this idea of going away from what is optimal if the world operates exactly as you want it to, paying a little bit when it did operate exactly as you wanted to, is pretty good policy in real statistical life in my mind. So a few more slides and I'll stop. If you only have the observed sample, build a prediction model. If you have propensities, fine, but if you don't, build a prediction model with whatever covariates that you can have available, certainly those that associate with the dependent variable. And these are empirically accessible. In other words, you've got a data set with a dependent variable and with covariates, you hope to have covariates. But then also put in ones that you think might either also or on their own associate with sample inclusion. Sample size being one, which you can always include, and a flexible function of it. These are not empirically accessible, but it doesn't mean you can't include them with a hope, if you'd like, that they will help. And if they associate with selection, you will actually improve the model in the sense of getting reduced bias, at least in the application. If you don't know the target population, you can apply that regression structure that you've built with those covariates maybe not with the sample size in there, but the other attributes that are at least available in a reference population, and do a weighted inference that will generally be better than not doing something like that. So my advice to both me and others is just do it. Obtain relevant information on the target population using big data, data melding, whatever you can to get at least what you think is a good set of covariates and a distribution of them for the target population. Design your studies, collect what you can, and especially collect things you may not think you need to do the inference within the data you're looking at, but might be very important for association with selection and therefore to be able to adjust for some of that. And do sensitivity analyses. And I'll close with the following slide, except for the thank you one that you've already seen twice, I think. I've been the last 10 years or so at least been educated on and participated in the survey world. And I think there's a lot of advantages in technology transfer between the statistical world, which used to be worlds apart from survey world. Let's begin to cross-fertilize and actually have those worlds become a really fuzzy boundary. Use data melding, and we haven't talked about it officially today, but harmonize data inputs as much as you can, combined by calibrating biases, building a Bayesian latent structure model to try to combine information at the lowest level that you would like to, but you may not see in every data set. And Sharon, Laura, and Raghu have come up with very nice examples of how to do that in statistical science. Measure attributes you may not need in meeting current study goals, but can help transport findings to another context. In other words, think about the public service aspect of this, where you're not only trying to do a good study of your own, but you may want to have your study be much more available for helping with other studies and other populations. Obviously, use administrative records and other big data to help identify these populations and attributes. Conduct aggressive sensitivity analyses. Never forget Xiaoli's and others that information may not increase with sample size. These wonderful examples of your performance may not increase, but it may decrease as you increase sample size if you haven't done a reasonable job of accommodating selection. And then there are lots of challenges in how to quantify variability in these melded, harmonized, big data, little data, medium data analyses. And Sharon, Laura, this is a hot link, which if you get the PDFs you can get, has at least some very nice ideas on doing that. And so I will hope that this was at least useful, and will say thank you.
Thanks, Dr. Lewis. That was a really interesting, intriguing, and entertaining talk. And thank you so much for sharing your insights on this topic. I'd like to open this up for people to ask questions. Does anybody in the audience have a question for Dr. Lewis?
I'll apologize early on for my incompetence at doing full screen on Zoom and not having the keyboard arrows working, but having to decide which of these things to do. But I learned. I learned.
Yeah, no worries at all. So I have a question. So I could see a lot of places where this would be very useful for my research, where I work with studies that try to obtain representatives as much as you possibly can from a self-selected sample, representative sample of the United States population in a certain age group. It's sociodemographically, race, ethnicity, so on and so forth. And so I could very, very easily see how what you're talking about, if we had access to a big data set to try to make inferences about the US population or some important segment that we want to focus on. Do you have advice? You mentioned some characteristics of the large data sets that would be desirable. Can you give a little bit more guidance on like the selection of, like, you might have a choice of different large data sets to try to use or leverage? Are there certain characteristics I should be looking for in that? Should that large data set then be more representative of the population than, say, my sample is, or what are some things I should be careful about thinking about?
I think maybe the prerequisites are that there are at least some attributes measured in a large data set that are not identical to the ones in your small one, or whatever you want to call that study, can be transformed to be used in the same way and become compatible, harmonized, or whatever word you'd like to use. And that, for me, that's the main prerequisite, is to be able to have a reference population that's more stable, and that you want to have as a reference population, with attributes that are at least as similar as possible in their definition and so on as the ones in your focus study. And one way to think about that in the design phase might be also, if you already know of some quote unquote big data or other studies, whether they're big or small, when you're designing your study, to think about at least making some of your attributes compatible with the definitions in those, even if you want to use slightly different definitions for your primary analysis, where you know that you need to define it the following way due to the traditions in the field, possibly include some other things or code things in a different way to get compatibility for this stabilization exercise. I think other than that, I'm rambling a bit because it almost comes down to just diving into the individual details. It's a little bit like, maybe not quite the same, and I'm not saying this to in any sense insult you, but, oh, Tom, could you tell me how to do statistical analyses or something like that? I don't mean it quite that way, but I think it really comes down to having to look at the details in each study where the strategic approach is to get compatibility as much as possible.
Right. And then you were recommending that the variables should be something that's potentially related to your outcome variable and or related to the selection probability into your smaller sample.
Let me go back here. You could have a situation, let's say, with your own study where you're not even worried about, where you don't have to worry about selection. I'll go back one more. And then you want to do this. I'm not going to go back all the way. You want to do the stabilization thing. It's not so much to just for the selection issues, but just to stabilize some of the inferences by taking advantage of stable marginals, if you want to think of it that way. In other situations where you may want that, but also have this concern that your study is, well, let's say you didn't design it completely, it's not a randomized study, or you're in a clinical trial where you don't randomize people to treatments. I mean, you do that, but you don't randomize people to being in the study. That's the case where you might want to be able to generalize to another population, and where you might want to collect some attributes that you think might be associated with selection into consenting, let's say, could then be helpful to try to externalize your results a little bit. And the reason I went back to this slide is that all of these and many other sites, but these are pretty good to give a lot of examples of doing it, not exhaustively, and maybe more exhausting than exhaustively. But so I haven't given a good answer, but I think or a complete answer, but I think it's hints on how to go about it, where if you look, for example, at Laura, at Raghu and Sharon's thing, you can see a lot of good examples about how to do that kind of thing. It's just one site that can do it.
Right. So I'll take a deeper dive into these papers. Thanks. So, and I guess before I forget, do you mind if I send you an email and ask you to share your slide deck?
No, and in fact, I think Seiko already has them. So
okay, got it. Okay, thanks. Okay.
Or I've heard that I can pronounce her psycho if I want to, from what she says.
So, does anybody else have any questions for Dr. Lewis?
Yeah, I do. I had so welcome, Dr. Lewis, to San Diego. It's really nice to see you. So I guess my question, first of all, thank you for this tour, beautiful tour of sampling and bias and variance and your compromise method. So my question may also be in the realm of, Tom, tell me how to do analysis. But
I shouldn't have said it like that. But.
No, I think this is probably even more so. But my question's a little bit. So more and more we have these prediction models that are used to decide who gets a loan, who gets sentenced, whether you're going to stop someone at a traffic light, policing. And I wonder if, some of that has to do with the training sets and poor sampling, and, they don't generalize well. And I guess I'm curious if you see a, your approach here seems very compelling, and whether you see an application there, and also whether, whether people are doing that, or is that?
Well, it's a good question. I think at least my first answer is, I would hope almost for anything we do in statistics, whether it be the well-designed randomized study or these things that are much more based on big data with predictions and algorithms on, that representation is the big issue. And so anything that one can do to improve representation in the design phase, but then also improve it in the analysis phase by bringing in some of these adjustments using whatever data sources you can, and anticipating the need for that when you're collecting your own data set, even if it's a design study, to think about wasting a few dollars to have some information that might help, even if it doesn't help you, help others take your study and suck it into theirs. And traffic stops and other things, I think having a discussion about what might be the big threats to representation, to generalization, to transportation, whatever word you'd like. And you may come up with variables or at least attributes that are not quite what you thought you needed for the narrow question that you're answering, but would very much help either you or others as you go on. Is that useful as an answer?
Yeah,
or?
yeah, thank you. I think so. I guess my part of it is that some of these models are already there and are being used already.
Oh,
so,
yeah.
So how to, how to draw back, pull it back a little, I guess.
But you may be able to do something with those that are already there by still being able, if you can open them up a bit, if they aren't completely locked down, to do some adjustments for reference populations, for selection and so on, either within the model or take the output if it's fine-grained enough and do it with the output. Again, I think it depends on what you're allowed to have in a way.
Thank you.
Karen, you have your hand up.
Yeah, well, I want to thank you for a really nice talk. I really enjoyed it. It's a lovely tour of this this whole area. I totally agree with the synergy between survey statistics and some of these bias issues that we grapple with. And I'm going to dive into these references. I see. So I work a lot in tobacco control, and there's a big fight going on over e-cigarettes in tobacco control.
I know.
Where the randomized trials show that yes, people quit. You give them an e-cigarette, and the observational data shows quite the opposite. That the people who are using the e-cigarettes are the ones that are struggling with quitting and don't quit. So there's a lot of interesting selection biases that are going on. One of the most interesting things, big takeaways from this for me, is that we can tell our collaborators to include covariates when they do modeling, include covariates associated with selection, even if it's not statistically significant in your regression. There are all these sort of practice rules of thumb that people use. And this should become another practice, another rule of thumb, another well-known reason for including variables. I think that could be a very useful sort of takeaway or thing to put out there.
Yeah, and can I make a comment before you go on?
I'm done.
I agree, but I also think it used to be the case that what we would do is, and still do and should still do, is to use these covariates to come up with a propensity score.
Yes.
And we should never speak against that in my mind. It's now a question more of how to use the propensity score. And so traditionally, or in the old approach, it would be weight by propensities. And I think now if you're a disciple of Rod Little, he would say, no, just do flexible functions of the propensity within the regression context and have that be the way that you try to work your way towards ignorability. And if you generally will end up with a little bit with a win in the sense that your variability will be less. The caution is that if your model specification isn't that good, you would have been better off doing reciprocal propensities. And so I think it's another case where keeping both viewpoints in mind in view is a good idea. Both approaches, I should say, is a good idea. And I'm not adding all the other things you need to do about doing distributions of propensities and getting overlaps and all that. But I think the point is we now have the added approach of the goal in any case is to make the selection as ignorable as possible in the technical sense of ignorable. And we can marshal more things to that end than we used to be able to.
I also want to say that we would love to have you come give us a biostats talk, and I'll send you an email next time you're in San Diego. That would be wonderful.
Okay, well, rumor has it I'm giving one on October 5th remotely.
Oh, so you've already,
At least I have it on my calendar.
Leon is ahead of me as usual. Excellent.
But
So-
I don't mind coming to San Diego at some point either.
Okay,
Niece
well,
and a
when you,
nephew and a few other hangers on there, so.
when you come,
October's a good time to come to San Diego.
we'd love to meet you in person when you come.
Well, I just like to thank you again. I personally found this talk incredibly useful, and I'm definitely going to also dive into the citations you gave in the slides. And I just like to congratulate you on a wonderful talk and a well-deserved emeritus. Hopefully you can relax a little bit.
Well, really, thanks for inviting me, and I've enjoyed presenting.
Yep, thank you very much. Thanks, everybody. Take care. Bye.
Thank you.
Bye-bye.
Have a good weekend.
Bye-bye.
Bye. Have a good weekend.